Okay. Hello, everyone. Welcome to the International Methods Colloquium. My name is Justin Essery. I'm an Associate Professor of Politics and International Affairs at Wake Forest University. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. This week's speaker is Matt Tyler from Stanford University. His talk is entitled Machine Learning Predictions as Regression Covariates, and this is joint work with Christian Fong, who's also from Stanford. Matt's talk will last about 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. You can ask questions at any time during the talk, but all questions will be held until the end of the presentation. A link to Matt's paper and slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I'll post those links right after this introduction. Now I'd like to welcome Matt Tyler to the International Methods Colloquium. Matt, welcome.
Thanks, Justin. Thanks for having me, and really excited to get questions and feedback on our work today. Yeah, so our work is machine learning predictions as regression covariates. So initially, this project was inspired by an empirical application of studying uncivil political dialogue on the internet. So what do we mean by that? So this is a screenshot of a very popular internet forum from reddit.com. So there's this politics subreddit. And so we're interested in understanding how users interact with each other, especially in terms of the civility of their conversations. So Reddit has their posts are kind of in this hierarchy. So a post below another post is responding to the post above it. So in this particular figure here, we have one user originally posted a question, and then the comment below it is actually attacking this person for kind of assuming their partisanship and launching an ad hominem attack. And so what we want to know is whether or not the community will respond to this particular user, Econ Man, and will the community punish this user. So our goal here is to estimate, in this setup, is estimate a regression coefficient where the outcome variable is the score of the post, which is roughly the number of upvotes, as in the likes by the community, minus the number of downvotes, the number of dislikes by the community. And the covariates here are going to be our incivility measure, so whether or not the comment or the post was rude. So whether or not Econ Man's post had ad hominem attacks or was targeting the other user in a non-substantive way. And then in this case, we're going to want to control for the mean score, so we're going to include a constant to induce an intercept term in beta naught. So that's the task we have in mind. And so what's interesting about this? The challenge here is that X1, this incivility measure, has to be hand-coded. Reddit does not provide us a measure of whether or not a post is rude or contains ad hominem attacks. So we ourselves as researchers have to go in and decide whether or not a post is rude or incivil. And this is particularly challenging in the Reddit case because there are millions of comments, and because the distribution of scores is so thick-tailed and has such a large standard deviation, there's a lot of noise. We're going to need to code a lot of these comments to actually be able to estimate beta with any sort of reliability. So one solution, we found and others have found is to hand code a subset of these comments. So to look, say out of a million, look at 1,000, hand code those, and literally go in and look at them and hand code them as rude or not rude. And then predict the remaining million posts, what their civility or incivility is, using an algorithm. In our case, we used a lasso, but you could imagine using something like a neural network or random forest. So we use this small 1,000 hand-coded set as a training set to impute the value of incivility for the remaining millions of posts. So this is sort of a common framework a lot of empirical political science and more broadly empirical social science is starting to get into. So this kind of approach has been done to study the differences between Russian politicians and military leaders in their speeches and their press statements, to study censorship in Chinese social media, studying whether the relationship between constituents and how that relates to the co-ethnicity of the constituent and their legislator and state legislatures, and then coding Supreme Court dialogue in the Supreme Court hearings. Yeah, so this is just a selection of papers from political science, social science that are similarly using algorithmic methods to impute a covariate or an outcome measure. So when we were first started this project, we realized that there's a problem, is that there could be error in our algorithm. In fact, there is quite a bit of error in the civility algorithm. The lasso or whatever algorithm we're using can't necessarily detect sarcasm, or it's not necessarily perfect at identifying whether or not an attack is directly ad hominem at the previous user or at some other part of the conversation. So to discuss this the sort of like measurement error problem that arises for us, we're gonna set up some notation here. So again, we have the same model. Y is equal to x prime beta naught plus some residual, and the residual's orthogonal to the covariate, just standard linear regression setup. And then we're gonna partition the covariates into x1 and x2, and then we're gonna say that the second element of the covariate vector x2 is always observed. So in our Reddit example, that was the intercept term, or the constant to induce an intercept term. And then because we don't observe x1 in a lot of cases, we're going to introduce these predicted covariates, partitioned to z1 and z2, where z2 is always going to be the same x2 covariates that we always observe, and then the goal of z1 is to predict or to impute x1. Okay, and so let's introduce just what we're calling the naive estimator, and we'll see why we call it naive later on, where you just plug in your predictions directly in for x. Okay, and you can do that, and you can rewrite the linear regression model like this without loss of generality, as y is equal to z prime beta naught plus a new residual. And then, just by the way we've set it up, this new residual is equal to the error x minus z prime beta naught plus the original residual. And so the question that we originally we're after is, like, under what conditions does this naive estimator actually, doing this OLS with a naive estimator actually give you a consistent estimate of beta naught? And this won't come to any surprise. You need the covariate z to be orthogonal to this new residual epsilon tilde. So you need that for consistency of OLS. So let's, because z and epsilon tilde have multiple parts, let's kind of break this down. So one, you're going to need an exclusion restriction. This predicted covariate should not be explaining what's in the residual from the original regression. Otherwise, it's going to be very hard to tell, what work in explaining the score is done by civility versus some other admitted variable. So you're going to need an exclusion restriction. And then you're also going to need something where we're just kind of shoehorning or categorizing as classical errors. So you're going to need the predicted covariates to be orthogonal to the errors. And so in simpler terms, what this means is that you need the regression of the error x1 minus z1, so the error in civility minus predicted civility. You need that regression of that on predicted civility and the other covariates to be 0. So in the Reddit example, you need the error to be mean 0, and you need the error to not depend on the value that you're predicting. Right? So this is what we're calling the classical error assumption. And so if you have both of these conditions, then just plugging in z for x will allow you to consistently estimate beta naught. So you don't need to do any sort of correction. If you just have the exclusion restriction and you only have part of the classical error assumption, so you only have that the error is orthogonal to the other covariates. So here in the Reddit example, that just means that the prediction error is mean 0. Then the naive estimator is attenuated. So there's a bias, there's a substantial bias, and it's inconsistent. So let's see this in an example. So this is just a similar notation in our Reddit example. So the score is going to be some intercept term plus slope times uncivility. And then suppose that we classify a post as civil or uncivil with 80% accuracy. So our predicted civility is equal to the true civility score 80% of the time. So that's pretty good. In our actual application, we do far worse than this. So with the exclusion restriction, you can actually work out what the bias is, and you can show that the expected value of the naive estimator is about 0.6 times the true slope, B. So that bias is sort of a reduction of 40%. In a slightly worse setup where your accuracy is only 70%, then the expected value of the naive estimator is about 0.4 B. So even though you still have quite a good, you still have quite good accuracy here, especially for a typical political science or social science setup, the magnitude of the bias relative to the coefficient you're trying to estimate is pretty large. It's on the same order of magnitude. And this is problematic, especially if you want to do some sort of hypothesis test of the slope being equal to 0. So this is, in our view, this frustrates sort of a lot of the scientific endeavors that people are coming into this with. So in our case, we wanted to see whether or not incivility could increase or decrease score. And then if we use a naive estimator, then we can't really rely on those hypothesis tests. All right, so that's naive estimator. So now we're going to talk about what we're going to do to fix that up. So like I said, the naive estimator requires both these classical error and exclusion restriction assumptions. And we think it's unlikely that classical error, that the prediction error is uncorrelated with the other covariates in the model and it's uncorrelated with the prediction itself. We think that's unlikely to hold in practice. And in fact, you can show that classical error is always impossible if the covariates and the predictions are categorical. This was shown by Eigner in 1973. Just to get some intuition for this, let's say you're trying to predict a binary variable. So if your prediction is equal to 1 for that observation, then the true value of the covariate can only be 0, 1. So you can't have mean zero error because the true covariate can't be 2, for example. It can't exceed 1. So the max of your error is 0, and therefore your prediction error can't be mean 0. So there's no classical error in that setup. So in that case, you're always facing at least some sort of attenuation bias. And then, like we said, attenuation bias makes it hard to find effects, which is a lot of what applied political science is. And then, perhaps worst of all, is that these inconsistencies make the confidence intervals meaningless. So even though we know there's bias, we can't actually, that's not enough. The confidence intervals we get out of that procedure don't actually cover the truth with any sort of, 95% confidence interval is not going to cover the truth with anywhere near 95% of the time. So we're going to present a method that only requires the exclusion restriction. We're going to obviate the need for classical measurement error assumptions. We're only going to rely on the exclusion restriction. We're going to do this without making any functional form. So we're not going to assume that we know the true data editing process in any way other than the exclusion restriction. And then our estimator is going to have the nice feature of being consistent and providing correct standard error, so you can construct confidence intervals with correct coverage. And we'll show in simulations that we do this. It's also going to account for the fact that you might be overfitting the predictions, predicted civility to actual civility in the training data. So we're going to present a sampling algorithm to deal with that. And then sort of the thing we're the most proud of is that this estimator is going to be more efficient than if you had just stuck with the data where X1 was coded. So if you said, okay, I don't want to worry about this prediction problem, I only want to use the data where I know I have the hand-coded true labels in front of me. The problem with that is that we're going to give you an estimator that can always beat that. So it turns out that having an algorithm is always better than trying to ignore the algorithm and sidestep it, provided the exclusion restriction holds. Okay, so what is our method and how does it work? So we're going to talk about our method in 3 steps. So the first step is we need to do some splitting of the coded data into what we're going to call training and validation subsets, and we'll dive into the details of that in a second. Then there's going to be a first stage regression using the validation subset. So this will remind a lot of people of instrumental variables and two-stage least squares. And then finally, to get this sort of asymptotic efficiency result, we're going to combine the coded and uncoded data using a generalized method of moments. Okay, so the step one, divide the coded and uncoded, the coded data into training validation subsets. So imagine you're starting with your full data set of N observations. So some of those, based on your budget constraints or how many RAs you have working for you, or how many documents there are, some of those data will be, some of those observations will be coded. So those are in our case, those are the 1,000 or so posts that are RA coded. So that we'll just call that the coded sample and their NC of those. And then there's the uncoded data, which to be consistent with the measurement area literature, we're going to call the primary sample. And so those, in our case, those are the 2 million or so other posts that we didn't have an RA code. And so in the primary sample, we only observe Y, we only observe the outcome, the score from Reddit, and we observe the predicted covariates from our algorithm. All right, going back to the coded sample, it's going to be very important to us to avoid this overfitting bias to only use some of our data for training the algorithm and use the other data for our two-stage least squares process. So we're going to divide the coded sample based on a random procedure. So there's no selection on covariates. It's all just a random sampling setup into a training sample. And then this is the training sample where we'll use features about the posts to train this Z algorithm. And then there will be a holdout validation sample. And again, this is we're using this term validation to be consistent with the measurement area literature. So this holdout validation sample will not be used in any way to train the algorithm. It will only be used to do the two-stage least squares in step 2. So your training sample might contain several different splits within itself, for example, to do cross-validation or to do a traditional train test split that a lot of machine learning algorithms are built on. But you cannot use the same cross-validation or testing sample. You cannot use that in the validation sample. So this is like a separate split before you do any sort of machine learning techniques. Okay. The training and the reason we do this is that because we want to avoid overfitting, we're not going to use the actual output of our algorithm, these Z values, from the training sample. So we use the training sample to fit the Z algorithm, the algorithm that produces Z's, but then we're going to hide its Z values from steps 2 and 3 to avoid overfitting. Okay. Okay. Now, why are we doing this? So in step 2, we're going to set up a first stage regression. So it turns out you can always find a set of regression coefficients for each element of X, so that you can predict X1 with Z prime lambda 1 0 plus eta 1, where eta 1 is orthogonal to Z. So you can always you can always regress X1 on all elements of Z. So for example, in the Uncivil case, the Reddit example, you can regress Uncivil on predicted uncivility and the intercept, the constant, and then you can regress the constant on predicted civility and the constant. Now here, lambda 2 will be sort of trivial. It'll be 0, 1, because you can always predict 1 with 1. And then we're going to compactly write this as X prime equals Z prime lambda naught plus eta naught. And then the nice thing here is that these errors, these etas, are going to be orthogonal to Z. Okay, why are we doing this? Because if you have the exclusion restriction, you can plug in these predicted values of X, these Z prime lambda naughts for X prime. So in this original regression where Y equals X prime beta naught plus epsilon, you can plug in Z prime lambda naught for X, just like you would in two-stage least squares. And this new residual epsilon bar is orthogonal to these imputed covariates from the first stage. Okay, so what this means is that if you knew lambda naught, then you can regress, you can find the true beta naught from the regression of Y on X only using Y and Z. All right, and so this is useful for us because in the primary sample, we own this uncoded data, we only observe Y and Z. And so given lambda naught, we can still identify beta naught in the primary sample. Now you might say, hold up, we don't know lambda naught. This is some unknown parameter. Well, that's why we split off a part of our hand-coded data into a validation sample. So we're going to use the validation sample to estimate lambda naught from this first stage regression. So for example, the kth lambda will be estimated via just an OLS of xk on z. Okay, so that's why we did this kind of three-part data splitting, where you need some hand-coded data where the relationship between x and z is not overfit, so it'll mimic the relationship between x and z and the uncoded data in the primary sample. Okay, so that's step two. And so now we need to talk about combining the coded and uncoded in an optimal way. So we have two ways to estimate beta naught. The first one is OLS on the training validation data. So in this data, we observe both y and x. We call this the labeled only estimator. And so this is just OLS, but we're going to write it in sort of a suggestive way. So this OLS estimator beta hat 1 is the vector of estimates that makes G1, this function G1 equal to 0, where G1 is the set of estimating equations from minimizing the sum of squares. So this is if you wrote out the sum of squares and you took its derivative and you set it to 0, this would be the set of equations that if you set them to 0 would minimize that sum of squares. All right, so this is just OLS written in suggestive form on the training and validation data, this hand-coded data, where we observe both y and x. That's one way to estimate beta naught. Another way is the way we developed in step 2 is via two-stage least squares. So you use two-stage least squares on the primary and validation samples. So given that lambda hat from the validation sample, you can estimate, you get beta hat 2 as via the G2 estimating equations, where the G2 estimating equations are just minimizing the sum of squares of the regression of y on z prime lambda hat. So again, this is just the derivative of the sum of squares set. It's just the function that if you set the derivatives of the sum of squares to 0, that's what the function you would set to 0. All right, so we can estimate beta naught either of these ways. We can get it via beta hat 1 or beta hat 2, via OLS or two-stage least squares. So if you're very conservative, you might say, okay, well, I should just use OLS on the training validation data because I know there's no bias there. I observe y and x, so I can estimate beta naught without any sort of problems. The problem is that the training and validation data will often be a very, very small subset of your data. So you don't want to hand code that much data because you have budget constraints, or in our case, there's millions and millions of posts, and there's more posts being made every second. So it's not really feasible to hand code all the data. So I think, okay, well, I have a lot more data in the primary and validation samples, all this uncoded data. So maybe two-stage least squares will work better there. It's true that you do have more data there, but it's not necessarily true that you will be just as efficient as OLS, because now you've introduced some error. Remember that epsilon bar from the two-stage least squares was different from the original epsilon, and it'll tend to have a higher variance because you are you're introducing this error between x and z prime lambda. All right, so you have here, one estimator that is, has sort of the per observation has the lowest variance, and then you have another estimator that has more variance per observation but has a lot more observations. So ideally, what you'd like to do is somehow combine these estimators, and we're going to show how to do that in an optimal way. So, like I said, we want to get some efficiency gains by combining the G1 and G2 estimating equations. So the easiest sort of way to do that in our scenario is through the generalized method of moments. And how the generalized method of moment works is you get your estimator by minimizing a quadratic equation, where this quadratic is formed by stacking the estimating equations G1 and G2. And then we'll talk about the choice of W in a second, but it turns out to not matter too much. What W is doing is it's a weighting matrix, and it's deciding how much to weight G1 versus G2. So for example, if this weighting matrix W put all of its weight on G1, then we're just getting the OLS estimator back. If W is placing all its weight on G2, then we're going to be getting the 2 stage least squares back. And what we want to do with the GMM is find some kind of like the optimal compromise between the G1 and G2 sets of information. We want to use all the data in the most efficient way possible. Okay, so it turns out GMM theory tells us that this estimator is going to be consistent and asymptotically normal for any weighting matrix W, any reasonable weighting matrix W, any positive semi-different weighting matrix W. And for the same reason that we would be consistent if we had just used OLS or we had just used 2 stage least squares before, because W is just sort of finding a compromise between those two. In the paper, we derived the W that makes the GMM estimator more efficient than using just beta hat 1 or beta hat 2. So there is a W out there that guarantees that in expectation asymptotically that the GMM estimator will outperform just using OLS or just using 2 stage least squares. And in the paper we show you how to get that. Right. So from here on out, we're going to use that optimal estimator. And that's what we're going to be basing our claims on. So in this third step, we combine the coded uncoded data in what we're arguing is the most optimal way. So to see this in practice, we're going to show you some simulations. So these are database simulations. So by that I mean we took the sort of like natural parameters from the Reddit example. We took like the means and standard deviations and the kind of estimated effect sizes, and we based our simulations on those sort of parameters. So the idea is that the simulation sort of mimics the practical reality that we're facing in our application. So there are 3 figures here, and let's focus first on the left figure. So this is evaluating over 10,000 simulations, say, the bias of 4 different estimators under consideration. So the first one, this black one, the legend's down here, by the way. The first one, this black one, is the naive estimator. So that's just regressing, that's just plugging in the predicted value of stability in for stability. The slightly lighter gray is the labeled only estimator. So that's only using OLS on the hand-coded data, the training and validation data. The slightly lighter gray is the GMM estimator. That's the third one. And then the lightest one will be the Oracle estimator. And that's the estimator that the unrealistic, impossible estimator that observes the actual values of instability. So we're using this as a baseline. So no estimator that we could actually use would be as good as the Oracle, but we want to get as close to the Oracle as possible. And so based on the theory that we've done on the previous slide, we want the GMM to be better than the labeled only estimator. It should improve on OLS, but it will its performance is lower bounded by the Oracle. Okay, so sorry, returning to the first figure, we're tracking the bias here, and we see that the naive estimator has a pretty substantial bias. And because we kind of a priori expect that the score will be lower for uncivil posts, we expect the community to respond harshly to rude posts. The bias here is positive, so the naive estimator is understating the effect of uncivility on the score. And you see that relative to the naive estimator, at least, all the other estimators have pretty low bias, and that's by virtue of the fact that they're supposed to be consistent. Going to the middle column, this is the root mean square error, and this is sort of tracking the trade-off between the bias and variance. Now, of course, because most of these the 3 rightmost estimators have almost no bias, this is mostly tracking their variance, whereas for the naive estimator, it's mostly tracking its bias. We see here is that the naive estimator and the labeled only estimator, the estimator that only uses the hand-coded data, are roughly equal in terms of the root mean square error. They're both hitting the true target about on average about the same. Whereas the GMM is getting much closer to the target here. So lower root mean square error is better. The GMM is getting a much lower root mean square error, so it's much closer to the true slope than relative to the labeled only the naive estimator. And in fact, so this is on the root mean square root mean standard error scale, but if you square everything, put everything on the variance scale, you can see that the difference between these bars implies that the GMM estimator is roughly equal to coding 16 times more posts. So instead of, I think we coded about 1,500 posts, it would be the same as if we had coded 1,500 times 16 posts. So it's a pretty substantial improvement over just using the hand-coded data, which we didn't think was obvious coming into this problem, that you could guarantee something like that. And then finally, you see the Oracle estimator has the lowest room square of all, of course, because it observes the true value of x. But the GMM estimator, at least relative to the label-only estimator, is doing quite well. It doesn't quite hit the Oracle, but it's doing pretty well given what it has. And then over here on the rightmost figure, we're looking at the confidence interval coverage of a 95% confidence interval, and you see that the three right estimators are all getting 95% confidence interval coverage as the theory predicts, and the naive estimator has sort of abysmal coverage in this setup. It's not even getting 12% confidence interval coverage. Okay, so that's a simulation. So let's actually apply this to our example. So again, the setup here is we have a bunch of posts depicted here on the left, and then we coded a bunch of them as civil or uncivil by hand. In this particular example, we coded the first three, but we didn't always just code the first three. They're randomly sampled which ones we coded. And then the rest of these posts, the majority of these posts are not coded. So we're going to rely on the algorithm to impute the value of civil or uncivil here. So we're looking in this data set, we have about 1,600,000 posts, and we split that into about 625 validation posts. And so these will be going into these will be in the first stage regression in the two stages of least squares. We have about 2,500 training samples. So these are what we use to train our algorithm, our Z algorithm, which I think we used a lasso. And then in our primary sample, this is the uncoded data, we have the remaining 1,620,000. Yeah, and so we took the 5,000 most common words in the posts, and then we, using a bag of words assumptions, we threw that in a lasso, and that's the algorithm we used to produce our predicted uncivility Z. In this particular case, we had a reasonable accuracy of say 60 to 70% somewhere in there, but by no means was it 99% or anything like that. So correcting for measurement error is going to be a big deal here. So here's what the estimates look like. So from left to right, we have the naive label-only GMM estimator. We don't have the Oracle here because we don't know the true labels. And we see that the naive estimator has a pretty narrow confidence interval because it doesn't realize that it has a large amount of bias. The labeled only estimator is we would expect to have less bias, but the problem with it is that its confidence intervals are much wider because it's only using a very, very small fraction of our data. In comparison, the GMM estimator is also supposed to be asymptotically unbiased. It's supposed to be consistent, but it has a smaller variance due to the fact that it's using all the data. It's combining all the data in what's supposedly the most optimal way. And then note that the GMM estimator is, so we should expect the naive estimator to be attenuated. So it should be, so that we should expect the true effect to be somewhere out here based on the naive estimator, because the naive estimator should be pushing it towards 0. That's what attenuation does. We note that the GMM estimator seems to be correcting for that attenuation bias. And so based on this, the GMM says that uncivil posts on average have about a 1.1 with standard error 0.2 lower score, which I think accords with at least the prior we had coming into it, that the community would respond to sort of unnecessary ad hominem attacks, attacks that didn't really add anything to the discussion. Okay, so that was application. So now we want to talk about the exclusion restrictions. So what about the exclusion restrictions? So yeah, like we said, relative to the naive estimator, the GMM estimator, it's bypassing most of these measurement error assumptions. So it's getting rid of what we call the classical measurement error assumptions. The remaining assumption, actually, the exclusion restriction, that is whether or not the predicted incivility is correlated with the residual from the original Y on X regression. You can actually test that in the validation sample, because in the validation sample you observe both Y, X, and Z. So you can actually just see whether or not Z is correlated with the residual of Y on X. You can only test that as the validation sample goes to infinity, so it's not the most powerful test, but it is a test that you can actually do, and you can have some sort of confidence that the assumptions are met. In our application, we didn't show you in the slides, but the p-values were 0.5 or something. That we passed all the tests. So unlike in instrumental variables, our exclusion restriction is more plausible because this z is actually, it's from an algorithm. It's fine-tuned to predict x. So we should actually, it's not trained to predict y and x. It's only trained to predict x. So you should really only expect minor violations of the exclusion restriction. You shouldn't, this isn't, this so-called instrument, the z is not being taken like from a textbook or something, or from some other data set. It's actually engineered, optimized to predict x, like in our lasso algorithm. We show in the appendix that the bias from violating the exclusion restriction actually decays as this error, this x minus z error, gets smaller. So the better your classifier does, the less of an issue the exclusion restriction, the less it matters. So you don't have to worry about it as much. So with all that said, you might wonder, okay, is there what if I do have the exclusion restriction still? Even if I have a super good classifier, I'm still worried about the exclusion restriction. Well, we are not. There are other methods out there that claim to not require the exclusion restriction. So there are non-parametric methods. For example, there's a paper by Chen, Hong, and Tamer, 2005. I believe the Journal of Econometrics, that they claim that their method will account for any arbitrary measurement error distribution, any relationship between y, x, and z. They're not looking at a particular problem. They're looking at kind of a different set, but you could, in theory, try and apply their estimator to our case. The problem with a non-parametric method like this that doesn't require the exclusion restriction is that it's not, because it's not using this sort of, it's not taking advantage of this linear setup where the exclusion restriction can have large payoffs. It's not root mean square competitive in realistic scenarios. So in our appendix, we show that these sort of like non-parametric arbitrary measurement error estimators have basically the same variance as the labeled only estimator. So this is of course anecdotal because we can only show you certain simulations, but based on what we've seen, we can't really recommend trying to apply these because they add very, very minor improvements over the least squares, the OLS, the hand-coded labeled only estimator. They don't really add anything beyond that. I mean, they're very small slight improvements, just because there is some theory showing that they will do better, but they don't actually do enough better to justify investigating or implementing these approaches in our view. They are certainly their improvements over the labeled only estimator pale in comparison to the GMM method that we advocated here. With that said, I don't know if we would necessarily recommend our method if you know the exclusion restriction is violated compared to this other method, but we don't think it's worth investigating these other techniques unless you run a simulation in your setup and you think that it will work well. All right, so in summary, we highlighted an algorithmic theme in recent empirical work across subdisciplines of political science and social science more broadly. That is, people wanting to use these algorithms to impute covariates or outcomes that they don't necessarily observe. We noticed that many practitioners are plugging in these algorithmic predictions, or they're using, there's some cases where people are using sort of ad hoc adjustments, or they're trying to like sample from a posterior implied by these algorithms. We talk a bit more in the paper about how some of these particular ad hoc adjustments don't work, but in general, the theme is that trying to use these predictions without accounting for the classical measurement error assumptions, it doesn't work. Your estimators are inconsistent. So to get around this, we provided a robust solution, and I mean robust in the sense that there's no functional form or homoscedasticity assumptions. It's robust to the classical measurement error assumptions, and it doesn't require you to take a gigantic leap of faith in kind of the size or the scope of your prediction error. Like I said, no functional homoscedasticity, And the thing that we're the most excited about is that it's always more efficient than just using the hand-coded data. So there's always some payoff to using an algorithm. So if you were worried that it was actually worth trying to apply a lasso or random forest to your problem to skimp on hiring more RAs, then we showed that it is always better to use an algorithm than to not use an algorithm, as long as you believe the exclusion restriction. Yeah, with that, that's the conclusion of the talk. And I look forward to getting your questions, comments, feedback, and thanks for having me.
Okay. Thank you, Matt, for that presentation. At this point, Matt Tyler is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And we've had a couple of questions already come in, so I'll go ahead and read those. Thomas B asks, given that your scores are thick-tailed and therefore the moments of the distribution under normal assumptions are biased, why use linear regression at all?
Right. So I guess our assumption coming into this project was that most people want to use or want to see a linear regression. So an applied work OLS is just sort of kind of the estimator of transaction. It's what most people use. So coming into this project, that's the estimator we wanted to focus on. We think it has a lot of interpretation in the sense that here we're just sort of estimating a difference in means, and so we're not really leaning on normality or the nature of the tails of the distribution in this case. There might be a more interesting way to investigate the distribution of scores and how that changes depending on the civility or incivility here, but and we're not averse to looking into that. But for this particular project, we were just trying to focus on linear regression because that's what most people use.
A question from EA. I assume that's not the game manufacturer, but maybe it is. How do differences in machine prediction accuracy affect your estimator? Does the label balance matter, and does it matter if the hand coding has error?
Yeah, so I'll take the last question first. So what we've been trying to do in this project, and I should have been a bit more forthright about it, is that we're dealing with the algorithmic error, the error from trying to propagate the hand labels to the unlabeled data. There is a very real and controversial problem with whether or not our hand coder, our RA, actually made good judgment calls about what's rude or incivil. That's a very important discussion, and I don't mean to downplay that at all. That's just not something that we're addressing here. So there are a variety of methods that look into coder reliability or putting bounds on regression estimates based on coder reliability or coder validity. And I encourage people to look into that, but that's not something we can really address here. We happen to think that in cases where the classifier does poorly, that the algorithmic error is probably more important in this unlabeled data than the coder error, but that'll of course depend on the case. Whether or not there's balance on the labels, that's something we haven't looked into per se. I will say that most of in our particular our application, that most posts are not uncivil. Most posts are civil, in fact. So we have I think something like 15-20% of posts are uncivil. In that case, we had to make a modification to our lasso algorithm. We had to kind of weight it differently to try and pick up those, but it didn't require any modifications of our GMM estimator. So our GMM estimator doesn't depend on the fact that the labels are equally likely to occur or something like that. I guess if you wanted to investigate how that affects the variance, you'd have to go into the variance of our estimator, which is included in the paper, but I don't know off the top of my head how that would interact with it.
Jessica Jones asks, what happens as you adjust the size of the training data set? 1,000 relative to a total data set of 2 million plus seems small relative to other machine learning work that I've seen.
Yeah, so I guess the way we're thinking about it is that the number of hand-coded samples you have is sort of exogenously determined by your budget or maybe your interest in the project. which is maybe another way to think about your budget. So if we just take the number of hand-coded samples as fixed, so going into this figure here, if we take the number of coded samples fixed, then the question is like, what's the optimal allocation of the validation and the training sample? That's something we wish we had a better handle on. So a lot of it's going to depend on what kind of algorithm you're using. That is what what kind of Z algorithm you're using to produce the Z's. So in our case, we had a lasso, which didn't require. It required quite a few cases to actually get off the ground and to do well. So we tended to load more observations into the training sample. But I think in general, it's probably better to put more in the validation sample because you need the first stage regression to actually, this regression of X on Z to perform well. So I guess my general recommendation would be only put in as many training, only fill up your training sample with as many observations as you need to get a decent classifier. Just sort of look for kind of a pivot, an inflection point or something in or an elbow in your performance graph, and then put the rest in the validation sample. Get as many validation samples as you can. Hopefully that answered the question. I'm not sure if I got it all.
I have a question. So I was surprised that you didn't make more explicit reference to the multiple imputation literature, because in many ways what you have is an ideal multiple imputation problem, right? You can have data that are definitionally missing completely at random because you can literally randomly choose observations in your data set to hand code, and then you can use some sort of MI algorithm to impute the rest. And my question is, given that this appears to be an MCAR kind of problem, why aren't we using the methods we know work quite well for multiple imputation on this problem as well?
Yeah, so I think that's a great question. That's something I wish I had time to talk about in the talk. So the problem, or at least the problem we have with multiple imputation, is that it requires you to make pretty possibly heroic assumptions about the data during process. So multiple imputation is sort of laden with a model, or at least some kind of attempt at a model of the joint distribution of your data. So for example, if you're using, you could use like a multivariate normal to do your multiple imputation, and you could say, well, my data is from a multivariate normal, and then I'm going to I'm going to draw from the distribution of my data as if it's a multivariate normal. We don't like that as much because that, then your sort of downstream estimates depend on your choice of a model. And we're very proud to have come up with a solution that does not depend on you assuming knowledge about your data during process. Additionally, when we have some simulations of the paper where we kind of like stress test this, and so how much does that actually matter? And they're in sort of the appendix of the paper. We just didn't find that multiple mutation, or at least the kind of the vanilla multiple mutation. I'm sure you could optimize it to any scenario you want, and I encourage people to do that, to look into like a custom multiple mutation setup for your problem. But if you just try to apply an out-of-the-box algorithm like Amelia to this problem, it performed pretty poorly, and we'd actually rather use just the hand-coded data than even try and use the uncoded data with multiple mutation in this case, based on the simulations, that is. So to reiterate, what we like about our algorithm relative to Amelia is that you don't have to make an assumption about the data in process. You don't have to come up with a model. Our method is entirely model-free. There are parameters in it, but these are linear projection parameters. They always exist, and we're not making any sort of assumption of that. We're not assuming that our data is drawn from the conditional mean function. We're not assuming it's linear.
One related question is, for Amelia, but also for something like mice, an important part of the MI process is incorporating uncertainty in the predictions into the final estimation. Yep. Using, you do, it's called multiple imputation because you impute it in multiple ways, and then you use Rubin's rules to to incorporate that uncertainty into the final estimate. And I'm wondering how uncertainty in your estimates of Z, I guess this would be, propagate through to ultimately uncertainty in beta.
So here we have the nice feature that Z, we're treating Z as a random variable. So all of its, all of the sort of, so the error in Z, that is like X minus Z, that itself becomes a random variable. So all that kind of variance is built into anytime we're taking moments or sample moments in our problem. There is some estimation uncertainty in the fact that you have to estimate these lambda parameters, these first stage parameters. And so we show in the paper how to propagate that error forward. And it turns out it affects the optimal value of W, this weighting matrix. So when you're weighting between OLS and the two-stage least squares components, you have to sort of downweight the two-stage least squares components because there's some error in the first stage. That's why I encourage you to put more data in the validation sample if you can get away with it. But mathematically, it's relatively straightforward propagating that error or putting that error into W and accounting for that error in the final standard errors of the GMM estimator. So that's all taken care of in the appendix of the paper. And the fact that Z is treated as a random variable, we're not taking the predictions as fixed or we're not conditioning on the prediction Z means that we're automatically accounting for the error, the variance from the inherent variability of Z.
It would be interesting as part of your paper. I know we're getting papers now have I think one of my papers got up to Appendix J. So I know there's space constraints, but I think it would be a nice thing to do to directly show from simulated data the relationship between the strength of what you would call the first stage model. Mm-hmm. In other words, how accurate or how uncertain those predictions are versus how uncertain the final beta estimate is. It would be nice to have a little graph showing, hey, look at how this propagates through and it actually works in the way that we intend.
Yeah. So there, that actually is in the paper now. It's not unfortunately, it's not in a very useful graph. We need to work on that. But we do see the pattern, and I should have talked about it, that if your classifier is poor, if you only have 60% accuracy, for example,
yep.
The variance is here, whereas if you have a classifier that is 90%, then your variance is down here. So
yep.
You do get the expected behavior that, the better you are at predicting X, of course, you're going to do better.
Right, which makes sense.
Yeah, so we're very happy that worked out too. Yeah, we need to work on presenting that better, and that should have been in the talk. I agree.
Well, we don't have any more questions from the audience, so I'm going to say thank you to Matt for being our presenter this week. I want to remind everyone that his presentation will be on our website shortly after this broadcast if you'd like to share the presentation with a colleague or watch it again later. I also want to invite everyone to join us on March 8th. When we will host Rob Carroll from Florida State University, my alma mater, for a talk entitled Choices and Their Effects. Please see our website, www.methods-colloquium.com, to get more information about this talk. Matt, thanks very much for a very interesting talk today.
Thanks for having me.
And I hope to see everyone next time.